Hi, I'm Daniel Tahara. I just finished my undergrad at Yale University where I worked with Dan Abadi on developing systems and techniques for manipulating semi-structured and unstructured data. And my presentation today is sort of the result of some of that work. Now this is a recording of a talk I gave at SIGMOD in June of 2014, and it is on Sinew, a SQL system for multi-structured data. So, in the past 5-10 years, we've seen an increased reliance on self-describing, evolving data formats such as JSON and JSON-like things, or sort of more generally key value pairs. And this has allowed developers to sort of code to their features without worrying about the structure of their data, since they can pretty much arbitrarily add and remove fields as they see fit. And this has allowed for more rapid, easier application development, and sort of because of this, we've seen this massive amount of data. We've seen an explosion of the amount of data that's produced by web applications. And sort of in parallel, we've seen the explosion of NoSQL database systems in order to store and analyze this data. Now, the problem is that performing analytics inside these systems is difficult because of the lack of a set of unified primitives. And sort of more generally, relational data and structured data is not going away. And it has become difficult because of these very specialized data formats or these specialized solutions to actually analyze the semi-structured data and unstructured data in the context of already existing relational data. So to sort of illustrate this problem, let's assume you have data stored in 3 separate data sources. You have relational data stored in a relational database that might represent customer data that you've collected from creating accounts. You might have a text database that stores email correspondences with your users, and then you might have a JSON data store that represents user interactions with your site. And what if you wanted to send an email to all customers who indicated a potential desire to buy in bulk with a deal on the items that they looked at? So let's explore how people have solved that problem. So the first option is what people call schema on write. And that's one that's been used for basically decades in data warehousing, and more specifically, I'm thinking of ETL. And under ETL, the producer of the data picks a sort of target schema, and then for each of the 3 data sources, extracts the data from each data source, transforms it and maps it into this sort of target schema, and then loads it into a single unified database. And in typical cases, that's a relational database. Now, the advantages of this approach are that the data is very easy to query later, because there's sort of a well-defined line or almost a contract between the producer and the consumer of the data in the form of this schema, this predefined schema. On the other hand, this sort of advantage is also a disadvantage because having a fixed schema means that ETL approaches and schema on write approaches don't handle evolving data sets well, right? So you can imagine that if one wanted to change the schema, not only would that person have to change the ETL code, but also sort of modify and manipulate the data that's already stored in the data warehouse. And so that's just kind of a pain. So the alternative to the schema on write approach, and one that's gained popularity, particularly with the rise of Hadoop and HDFS-based systems, is what's called schema on read. And in schema on read, you basically store your data in its raw format in HDFS. So, JSON data is stored as JSON, text data might be stored as text, etc., etc. And then, sort of at query time, the person doing analysis specifies to a query engine how the data is structured and how it should parse it and interpret it and map it to some relational structure. So, how might this work? For relational data, obviously it's straightforward. You just sort of let it be as is. And for unstructured data, you also probably just load it in its original format. But what about semi-structured and key value data? So looking back to the data set, the JSON data from our original slide, one approach might be to shred it. And shredding is something that sort of conceptually has been around for decades and was used in a lot of early XML databases. And basically what that means is for every object in your data set, you divide it into separate tuples where each tuple has a reference to your initial parent object, whether from some ID, and then as well as a key value pair from that record. And so what you end up is with this sort of tall, narrow table. Other approach, on the other hand, might be, you might say, oh, I want a row in my database to correspond to a single object in my original JSON dataset. And then, you'd figure out some mapping from the columns of your relational schema to the keys and the values of your original JSON data. And so the point I want to make is not that one or the other of these approaches are correct. It's just that these are two of sort of an infinite number of ways of mapping semi-structured data into your relational schema. And so while this mapping and structure is adaptable at query time because of the way schema-on-read systems are built, it places a large burden on the person doing analysis, because that person actually has to, at some point, understand and reason about the structure of the data. And for this reason, it doesn't lend itself very well to data exploration, where you don't actually have an idea of what your data looks like and you're trying to get a feel for it. Because you're the one, as the person doing analysis, who has to actually define the schema that you're querying against, right? Okay, so our goal then is to create a system that preserves the advantages of both systems. So the ease of querying of ETL-based systems and this clear contract, as well as sort of this flexibility afforded by schema-on-read systems. And it does so through the automatic generation of a queryable schema. And because of this, Sinew can offer the full range of SQL primitives. So what that means is, not only can you analyze your relational data using SQL, and if that were the extent of what Sinew can do, I wouldn't be giving this presentation, but it also means that you can use SQL to analyze your semi-structured data and your unstructured data. And you can do all of this, while actually retaining traditional transactional semantics and all the acidity guarantees, because Sinew stores all of the data that it manages inside a relational database. So that's an important feature that differentiates it from other systems. Now, sort of lastly and most importantly, we're in our design particularly interested in systems, in situations and environments where data warehousing infrastructure exists, and particularly in the form of a row store. And this isn't to say that column stores aren't used or aren't gaining popularity, but by and large what we see is that sort of the main warehouses are dominated by the likes of Teradata, the likes of Oracle, and IBM, and particularly their row store versions. So our design is built in such a way that it can extend a relational database without requiring any modification to relational database code in order to provide the feature set that we described. And in particular, we're focused on the case of row stores. And so, the point I want to drive home is that we're not trying to build a system from scratch, right? If we were, we would do a lot of things differently. We may or may not have started with a relational database, et cetera, et cetera. And instead, the research question at hand is if and how we might be able to add support for semi-structured and unstructured data to a relational database through a layer that would sit above it. Just a high-level overview of the rest of this talk, I'm going to spend the next couple of slides, the next couple of minutes, highlighting sort of the major conceptual components of Sinew's design, and those are the universal logical schema, hybrid physical schema, dynamic column materialization, text indexing, and search. And then I'll show some benchmarks and conclude. So, as I mentioned, Sinew differs from previous systems because it automatically generates a queryable schema. So, obviously, the first and most important choice in our design was the design of our system was what logical abstraction are we providing? What is the schema that we're generating and presenting to the user? And so, as you probably can guess given the title of the slide, we borrowed from the universal relational model in our logical schema. So, what that means is the relational parts are just sort of mapped as is. You keep all the columns that exist. And the unstructured data is just loaded into a single column, usually probably a text type. And then for all the JSON or the semi-structured objects, every key is exposed to the user as a column that can be queried and manipulated as if it were part of a relational schema. And so, in some senses, it's like very minimal and easily queryable. And so, in order to answer the question I posed on the first slide, all you'd have to do is perform this query, right? You have a couple of column references, a couple of predicates, and that's it. There's no complicated regular expressions, etc., etc. And now, sort of one of the important things about JSON and semi-structured data types are that they allow things like nesting. And in this system, basically any nested key is referenceable as a column, and it can be queried. All that has to happen is the name is basically the concatenation of the parent object with a dot notation and followed by the nested key. And not just the nested keys, the nested object itself can be queried as sort of an atomic entity and retrieved as a column. So, this is a universal logical schema is a nice virtual abstraction. It's a nice logical schema, but it's actually a poor way of storing things physically, in particular because of the overhead and maintaining a large number of columns in what we call a wide table. And sort of this goes hand in hand with another problem that we face, again, particularly for row stores, in that sort of the lax structure of these semi-structured formats comes with a cost, in particular sparsity. And so, what happens when you have a lot of sparse keys in your data set is that if you try to store all those things in a wide table in a row store, you end up with a lot of wasted space because the relational database will either reserve space in the tuple for a value for each individual column, and if it's null, it just has this wasted space, or at the very least, it'll have a bit or a byte in a header that indicates that a column should exist, but it's null. And column stores address a lot of these issues, but again, that's not the case we're targeting. And if we were building a system from scratch, we wouldn't start with a row store. So, sort of in the context of our problem, what Sinew does to sort of deal with the sparsity problem is to separate columns in the logical view into two categories: physical columns and virtual columns. Physical columns, as the name suggests, are columns that exist in the logical user-facing schema but also appear in the underlying relational database schema. Virtual columns, on the other hand, are columns that appear in the logical user-facing schema but don't actually have a physical analog when the data is stored in the relational database. Instead, these virtual columns are serialized along with all the other virtual columns into a special column that we call the column reservoir. And basically that's just a binary serialization of all these columns. So going to looking at the semi-structured component of our data set, product name and price, the first columns might be physical columns, and then tags, color, and action might be virtual columns. And so the underlying relation might look something like this. And so importantly, what this means is that as new keys appear in the input data, say on a subsequent load, we can actually present those columns in the logical view and sort of like logically add a new column to our user-facing relation without actually having to make physical changes to the database. And this is because all that has to happen is sort of on a load, when Sinew identifies that a key exists for which we don't have a column in the logical view, all that Sinew does is sort of add an entry to its catalog indicating that this new virtual column exists, and serialize this new key value pair along with all the other virtual columns in the column reservoir. So this allows us to present this sort of flexible, evolving, automatically generated user-facing schema without too much cost in the underlying RDBMS. So modulo some query rewriting, I think it's pretty easy to see that this universal logical schema along with this hybrid physical schema provide us with the functionality and the feature set that we desire. And sort of in some benchmarks that we ran, there actually isn't much overhead to referencing a virtual column as opposed to referencing a physical column. It was only about 1 or 2%. However, sort of the problems arise when you start to try to do more complex queries like joins, like sorts, because these queries really rely on the RDBMS optimizer to produce efficient query plans. Now, when, for physical columns, this is obviously not an issue, right? Because the optimizer keeps statistics on all columns in the database. But virtual columns, because they're sort of serialized in this special nested binary column that we've come up with, are entirely opaque to the relational database optimizer, right? So basically what happens is when the optimizer tries to, compute some join order, it has to assume some fixed random selectivity, and in Postgres' case, its favorite number was 200, even for a 64 million record data set. And it takes this number, and then based on that, it assumes the selectivity is very low and computes a join order accordingly. And in this case, you end up with a huge degradation in performance. So what Sinew does to address this is to sort of dynamically and selectively materialize virtual columns into physical columns, and it does this based on factors such as sparsity and frequency of reference. So let's say, for example, that Sinew decides that action should be upgraded into a physical column. Basically what would happen is a process would come, change the underlying physical schema and add action into the relational database schema, and then it would iterate row by row and look for a value for action in the column reservoir, and if it exists, move it to the physical column, and so on and so forth. Now, an important feature of this design is that it's entirely incremental, and it can be stopped at any point in order to free up resources for incoming queries, because there obviously is a cost to trying to do a column materialization concurrently with an incoming query. Now, it's not immediately obvious. Let's say we stopped here, right, in our materialization process. It's not immediately obvious how Sinew can maintain consistency in the face of sort of partially materialized columns. And in order to ensure consistency, Sinew basically has a mechanism that says, okay, when it sees a query for a partially materialized column, it'll check both columns for values. The physical column followed by the virtual column, and if the physical column has a value, it'll return that. If it's null, it'll look in the column reservoir for the virtual column. This, combined with the fact that updates are always applied to a physical column if it exists, which ensures that the physical column always contains the most recent version of the data, if it has data at all, sort of together ensure that we can maintain consistency in the face of incoming queries, in the face of incoming updates when we have partially materialized columns. Now, it might not be immediately obvious. I'll refer you to the paper for a more detailed description, but that's what Sinew does in order to deal with that case. Now, the last piece of our vision in our system was sort of the ability to support queries over unstructured data through SQL. Right? Obviously relational data we can query just sort of as a matter of fact and just what a relational database is. Semi-structured data is now queryable through the couple mechanisms that we described. And so, the question is, how can we handle unstructured data in a relational database system? So what Sinew does is it includes a text index, which can be queried from the relational database using a user-defined function. And what this allows is that, you say you load your unstructured data. This unstructured data gets sort of not only put in the underlying relational database column, but also gets indexed in this text index. And then using this UDF, you can perform text queries over this unstructured data. And because we're using a text index, we get sort of a far more expressive set of predicates than we can from a traditional just relational database operators. And sort of moreover, we actually, if we not just index our unstructured data, but our semi-structured and relational data as well, we can do things like perform text queries over all columns in the database, over all columns in the logical schema, and not just looking at a single column. And so we can do this sort of much more expansive set of operations than is afforded by a traditional relational database just by adding a text index. Now, that's the first use case mentioned on the slide. The second, the other upshot of indexing text data in a text index is that we can use it to improve performance on other queries, and in particular, references to sparse virtual columns. So I mentioned one of the problems with these virtual columns is that they're opaque to the optimizer. So what happens when you want to perform a predicate is that, at the very least, the execution plan will have to include a full scan of the underlying relation, because it has to iterate row by row, extract the virtual column, and then evaluate the predicate. What a text index allows us to do is to actually delegate that query, that predicate, to the text index. And since the text index allows us to facet our results by field, which basically corresponds to a key value, a key in a semi-structured data set or a column in our relational database, we can actually use the resulting set of row IDs as a filter over the remainder of the query. And so that actually, if the predicate is particularly selective enough, allows us to save a lot of work. So I mentioned now here are some benchmarks. Basically, what we were looking at in constructing our benchmarks was we were looking to compare Sinew against systems that could perform a similar set of operations modulo query rewriting. So basically, you can query structured, semi-structured, and unstructured data sort of without ever having to define a schema at any point in the process. And in addition, we were looking for systems that could handle both reads and writes. So that left us with only a few options. And so those three options were a NoSQL database, right? So you can imagine modulo some query rewriting. You could do all the things that we just endeavored to do. So for our NoSQL database, we chose MongoDB. We looked at and found relational databases with JSON extensions. So those options basically, were IBM DB2 or Postgres with its JSON extension that's a part of Postgres 9.3 and onward. And so in this case, we chose Postgres. And the other reason for choosing Postgres over DB2 was that our prototype system is built on Postgres, so that gives us a real good apples-to-apples comparison and see what the effect of our system design is. And then lastly, we have a shredding-based system, which we call the EAV system for element attribute value, which is sort of the traditional canonical way of mapping semi-structured data into relational tuples. And so that was our third system. Our benchmark set was the NoBench query benchmark that was developed at the University of Wisconsin by Jignesh Patel and Craig Schlosser. So thanks to those guys. In addition to an update task that we added. This update task is included because we're also interested in write performance as well. Now, the benchmark queries 1 through 10 are presented here. Query 11 is a join, and I'll show that on the next slide. The query sort of comprised references to dense columns, references to sparse columns, included selections, projections, aggregations, and as I mentioned, a join. And sort of, I detail a lot of the exact details. Obviously, I detail the results in the paper. But sort of the high-level point is that Sinew outperforms each of the three systems, and I'll sort of explain why for each system. For MongoDB, despite this sort of flexibility afforded by NoSQL systems, doesn't have good scan performance and doesn't have good column projection performance. It's very good at single key sort of ID, single record lookups by ID. But when you want to extract a single key from all records, it doesn't handle that well. Because basically for each record it needs to sort of scan its object and look for the existence of the key, whereas in Sinew we can take advantage of the fact that we're storing things in a relational database, so all you have to do is a tuple lookup, right? Now, versus the Postgres JSON system, what we see is that similarly to keys stored in our virtual columns in the column reservoir, JSON keys are opaque to the optimizer, right? So a lot of times the optimizer produced bad query plans, which resulted in sort of poor performance. In Sinew, on the other hand, we get to take advantage of this dynamic column materialization where some of these virtual columns are upgraded into physical columns, in which case, the query plans are fine and extraction is very easy. And then lastly, the EAV system is just basically slow, independently of Sinew's performance, because this mapping creates a lot of redundancy in your data, and you actually end up with this data set that is about 2.5 times the size of the original data, and so there's obviously a large disk overhead there. So those were the more simple queries. Here is the join and the update task, and sort of the important points from these are, obviously MongoDB lags significantly behind Sinew and Postgres JSON on a join, and this is because, as I mentioned in basically the very first slide, there is not a good set of analytics primitives in relational database and in a NoSQL database system, and in particular, there's just no join support, right? So I had to code some custom join code in JavaScript, and even if I had gotten it perfectly, I imagine that there were some kinks to it. Even if I had written the most optimal code, it's still not gonna get rid of this 2 order of magnitude difference in performance. And then sort of lastly, the update task was sort of interesting because it allows us to see what the transactional overhead is in Sinew. Like what do we pay over a NoSQL database system for storing our semi-structured data inside a relational database? And you might expect that that MongoDB would outperform Sinew in this case, but what we actually saw was, yes, there does exist some transactional overhead, right? It was actually about 10% of the performance, but this transactional overhead doesn't come anywhere close to overcoming the difference in Sinew's performance on column projections and selections over MongoDB, right? So our update task updated certain records based on the evaluation of a predicate, and because of this, Sinew outperforms MongoDB. So, in summary, Sinew provides SQL over relational, semi-structured, and unstructured data, and in particular, it does this by sort of inferring a schema at load time and presenting it to the user at query time in the form of a universal logical relation. And sort of lastly, and most importantly, its system architecture sort of extends a relational database without ever modifying RDBMS code. And so you get this support for semi-structured and unstructured data as an extension to an existing system, and it can be built on an existing system. So with that, if you have questions, feel free to email me. Note that this email address is different than what's listed in the paper, and further resources are listed here. Hope you enjoyed the talk. I'm Daniel Tahara. This is Sinew. Thank you very much.